I think this whole workshop is about how do you go across these scales here. Maybe everything so far has happened here, and I think the first apology I need to make here is that I'm going to move away from this, and I'm going to ask you to imagine that, so yes, we're interested in electronic structure, but actually not really. Suppose we really care only about the mechanics and want to forget about electronic structure. So this whole talk will be about that question. As I try and go up the scales, how can I forget everything that happened in the high accuracy models in principle? And the canonical question to ask here is, I want to do simulations, molecular dynamics, molecular statics, whatever you want to do. I only care about the mechanics, so I want to do simulations with this potential energy landscape that the electronic structure gives me because I trust it, but I don't want to pay the price, right? And so how can I go and construct a surrogate model for that, an interatomic potential, a force field, whatever you want to call it, that gives me everything, I'm not used to this anymore, apparently, that gives me everything that my high fidelity model gives me, but at much lower cost. Okay, and so that's a question of this. That is multiscale modeling, that is coarse-graining. People have been doing this for 100 years, right? And so where this talk comes in is where sort of, I would say around 2005 onwards, with more computing power, and people discovered, oh, there's this thing called machine learning. It can help us do all sorts of things, and a huge number of people started working on that. Many different ideas, and I cannot possibly do justice. I should probably keep writing this, and eventually the names come out the bottom of the slides. I apologize if there's somebody here who I should have mentioned. Stefan Kmiele, I have no idea who it is with the masks on, but I think he's giving a talk on later this workshop, so I'm looking forward to hearing that. I've just had a chat with other people about. So there's it's basically I think since 2005 onwards, first slow and then fast, a big push on really closing this gap between interatomic potentials and electronic structure potential energy landscapes. Okay, but it's not just about that, right? As I said, it's this entire sort of scale that is really of interest to people, and for example, you can also talk about this step here, right? So I guess the question that people are asking a lot is, what is the exchange correlation function? That's the same kind of coarse-graining question. Something that I will talk a little bit about towards the end of my talk is if I have a good model here, but I really want to go into a semi-empirical domain for computational cost, right? How can I do that step in this sort of semi-automated way? One of my former postdocs says he really wants to use this for coarse-grained molecular dynamics, right? And so in this case, when you coarse-grain a dynamical system, then you get this friction operator in here. And so is that something that we could automate? Right? No longer pen and paper, but actually fill in these gaps using our machine learning models, for lack of a better word for now. And so everywhere the same questions arise over and over again. And while I will start with that red line here, for the first half of my talk, I then want to quickly sort of spread out a bit and talk about some more ongoing questions and projects to talk about. Okay. So with that in mind, and also keeping in mind that I'm a mathematician, I'm a numerical analyst, that remains my main interest. As much fun as big computing and actually seeing things move around in real models is. I want to. This talk will be about what can I say sort of rigorously. That will be the main topic. So I really want to be able to explain from the beginning to the end, maybe under simplifying assumptions, what can I really prove about these models that we're constructing. So for that purpose, I will not talk about neural networks, because I don't work on them, but the reason is because this is just something where theory is a bit behind. And I like linear models. That means I can really understand every step along the way. I have full control over the regression, the parameter estimation task, and so on and so forth. And so this talk will also be about linear models, not about artificial neural networks. And lastly, what I just mentioned, it's not just interatomic potential. There's this whole range of coarse-graining problems. And so in all of these, you have, what you mean by a particle system, it means something slightly different. The kind of symmetries that you have change. And so that's the other thing. I want models that are very flexible and I can adapt very easily to a new situation, to solve new problems. Okay. So that's the general setup. And so now for the next 15 minutes or so, I want to introduce one specific method that I've been spending a lot of time on, understanding, implementing, improving, which is called the atomic cluster expansion. We'll get to that. And nowadays I think it's not just one out of many methods. I think it's inevitable. And I want to explain now in the next few slides why I think this model really is inevitable and canonical and could play a big role going forward in this field. Okay, I forgot who it was. Somebody said my role is to over-exaggerate the importance of my field. Right? So there we are. There you go. Okay. So that's what we're doing. So step one, we want to construct these potential energy surfaces, and the first thing that is, and I think anybody who's thought about this field, a few of the things I'm going to say are completely obvious. I'm going to say them anyway. So imagine this is not a 2D but a 3D simulation, right? Maybe even a bit bigger, but then we can't see the atoms anymore. So we want to perform large-scale material simulation. That's our task. That are not reachable with DFT. Okay, so we want these surrogate potential energy landscapes for that. And the first obvious observation is if you parameterize the full potential energy surface, you cannot. You can't even generate the data. These would be far too high dimensional. We don't even get started. And so it's sort of the obvious, but still, I think, important, the non-trivial first step was by Bela and Parinello, 2007, to say we should not parameterize the full potential energy surface, we should parameterize the site energies. So, of course, if you do interatomic potentials, that's what you do. So you split your potential energy into contributions from individual sites, and those you then parameterize. And so the reason this is so important, because now these objects that have a very small finite horizon. And so what that means is you can estimate the parameters by training them on small configurations. So configurations that are sort of on the order of the cutoff radius. And when you do, and then you can say, okay, I can now, once I have the site energies, then I can run simulations on large domains. I think it's a hugely important and maybe not always fully appreciated point. And then, of course, as Alex announced in his first talk, a lot of the questions that arise now is, well, interactions are not short-ranged. Why can you do this? But we'll get to that much, much later. For now, let's just assume they are. We are in a simple material, right? Some certain phases of silicon and carbon, things like that, for the sake of argument. Those are the parameters. So I'm saying I split my total energy into site energies, and then I parameterize the site energies instead of the total energy. Yeah. Okay. And so that's the first question that I would ask mathematically. Why can we do this? So I usually show a slide that shows some toy models that we're proving this for. I can never find enough space on my slides, so I put it here now. I'm sorry if you're online. But I'll keep this up because it's sort of, yeah. Think of, with my group, we don't really work with sort of proper electronic structure models like DFT or beyond DFT, partly because this is extremely technical mathematically, and it allows us to experiment more if we stick with tight binding type models. So, but basically the results I'm going to show you are true for anything from classical linear tight binding models to DFTB, or even if you simply take Kohn-Sham DFT and discretizes with atomic orbitals. So not all results will be true for all of these, but somewhere in between, and I will say which ones are true when. But for sure, everything I'm going to show you would be true for linear tight binding models. So these, for example, these classical tight binding models for carbon or silicon, something like that. And so, for example, one result you can very easily prove is that these site energies are in fact local. So I'm saying these site energies, because they're not actually uniquely defined. There is no unique way to decompose the total energy. But what I'm saying is the result is there exists a way to decompose these total energies in space into pieces that are truly local and even exponentially so. And so now the question is, you can ask, okay, what's that crucial parameter C in here? And essentially you can prove that it scales like the gap plus 1 over plus Fermi temperature, right? So that's the kind of results you can prove here. For what it's worth, the technique you use is rational approximation. I learned this from Lynn's PhD thesis, but I think it's used quite broadly. Okay, so this is the kind of result you can prove. For me, the most important part of that actually was the following statement that, if you have a gap here, then you say, okay, but now I put in defects in my solid, and now I get all this pollution in the gap. What does that mean? And in fact, it does not affect it. So it's only the gap in the bands that matter, not the spectral pollution, not the pollution that comes due to, for example, point defects. Okay. And just to emphasize also, this is a result that is true not only for linear tight binding models, but also nonlinear ones. So all the way up to DFTB. Provided, this is the key caveat now, if you explicitly put screening into the Hamiltonian. So if you basically, instead of a Coulomb potential, put a Yukawa potential here. Again, we're sort of assuming everything is short-ranged a priori already, and I'm pushing that question to the end of my talk. Okay. All right, so that's justifying step 1 of these machine-learned interatomic potentials. So what that means, namely, is that once you have this, you can quite easily prove that you can take these site energies on the full quantum mechanical model and approximate them by localized site energies, namely the interatomic potentials. And that's now our first approximation parameter, the cutoff radius. But now, for the vast majority of models that I've seen, even for the simplest possible materials, you would still end up having 30 to 100 particles within that cutoff radius. And when you're talking about low-dimensional approximation, this is not it. Right? 30 to 100 particles, that gives you 100 to 300 dimensions. That's still not a trivial task. And so somewhere you need to find low-dimensional structures, or at least low-rank structures. Right? If you talk to Reinhold, he'll say you don't need low-dimensional, low-rank, but in some form or another, you need to reduce the dimensionality. And the simplest and most obvious idea to try here would be the body order expansion, right? You replace your site energies now with an expansion in constant 2-body, 3-body, 4-body, and while you're at it, go all the way up to n+1 body interaction, that has so many advantages. Obviously, it reduces the dimensionality, right? So if I can truncate this, maybe I cannot, right? But that's the question. But if I can truncate this expansion at an order that is much lower than the number of particles I have, right? Let's say I have 30 to 100 particles in my atomic environment, but I can truncate this expansion at even 5 or 6, then that's a phenomenal reduction in dimensionality. Yeah. And the second one, conceptually, for me, if I'm interested in sort of an approximation result, right? If I work on the site energy, then the input here is a set. But these objects here, those now live in Euclidean space, and so you can start really talking about how do you actually construct these approximations. Whereas here, that's much more difficult. Okay. Right, so now the question is, can you justify this truncation? And depending on who I talk to, I get completely different answers on, could such an expansion ever converge? Right? I don't know, if I pick a random person here, I have no way of guessing what they will say. But many people are very cautious. They will say, actually, no, it cannot possibly, and then we explain why. And so the caveat in that is that usually when people think about this sort of expansion, they think of a vacuum cluster expansion. They think of this contribution here to be some form of an energy of a cluster of n+1 particles in vacuum. And that's a bad idea, because then you completely change the chemistry. So, Gero, you have a question?
So Christoph, I have a question. Maybe I missed something. I thought your previous result, this localization result on the site energies, is precisely such a result that justifies a few-body expansion, because the site energy is just kind of a, it's just a k-body term where k is the number of atoms in your region until the decay has set in.
Right. So, are you happy with a 30-body?
Yeah, I'm happy with it, but I'm sort of saying, are you now trying to simplify on top of it? Or?
Yeah, I'm trying to go even down further. I'm trying to go basically, let's say, from 30 atoms in my interaction range down to 5. Yeah? No, but that's the goal now. Right, so I'm saying this, I already have simplified the model by going to not millions of atoms in my model, but only 30 to 100. And now I'm going to reduce it further by going to this n terms, at most n terms at once, n particles at once. Yeah? And that n could be 3 or 4 or 5, I don't know. Yeah. Okay.
So if I had some small number of particles in vacuum, right, then I could sort of uniquely define these terms.
Yes.
But are you doing that here?
No, absolutely not.
That's what I thought, right?
So I'm specifically not taking the vacuum terms here. If you do this, then sort of this concern that I talk about here is absolutely true. If I took vacuum terms here, I would not be able to prove this result. Okay, and it's very, very, very limited. This is a very modest result. It's just the best we can do at this point in time. Okay, so the result is that when you truncate we call this correlation order n, because there's a central atom and then there are n atoms in the neighborhood, so it's n+1 body. But anyways, we call it correlation order. You have an exponentially small error. Again, okay, it's for a specific subclass of these kind of tight binding models. That's the restriction. And for now, it's just linear. And again, this is something I'm going to push away for later on how to deal with that. This is extremely interesting. But so again, exponential. Again, this parameter here depends on the band gap and the Fermi temperature, depending on which one you have, or both, I don't know. But now this is not my problem. The biggest concern I have here is that this is only true uniformly for all configurations within one crystalline phase of the material. So for example, if I go from one phase of silicon to another phase, both are insulators, I might not get that. And the reason is that the band gap goes somewhere else. And the techniques we use to prove this comes from potential theory, and it's really difficult to bring this together like that. Okay, so this is a problem that I'll address later. It's very interesting how we address it, I think. But for now, let's still accept that and say, okay, we can do this in principle. What do I do?
So I should just ask my question?
Yes, go ahead.
Yeah, I'm a bit confused about your comments on contrasting the previous results with vacuum, right? Because if you fix the background, isn't vacuum just another background? So, I mean, you can prove a similar results for vacuum, I suppose.
You're talking about this result, right?
Yeah, and in the previous slide, you are saying that because people are using the vacuum expansion, so that
the statement is this.
Some confusion.
The statement is this.
What
if I define epsilon n of this group of atoms to be the energy of that cluster in vacuum, then this result, I'm not saying it is false, but at least I cannot prove it.
Okay. Oh, you define this in a vacuum, but you use it for in the periodic solid. That's what you mean?
The way you can think about this is that this is an energy that somehow magically sees that it's in the environment of a periodic solid. That is the way to think about this. And if you want me to that I pin.
I see what you mean. Yeah.
Yeah.
So you mean that the construction should depend on the background.
Exactly.
So it's like embedding theory.
That is the statement, yes. And that's also why there is this constraint here that I can't even switch across phases with that result.
Yeah.
Yeah.
Makes sense. Thanks.
So I guess, so basically what you're also saying is that if you had a semiconductor cluster, right, you wouldn't be able to prove this.
Okay, would it be true in a cluster? That's a good question. I think it should be. I'm not concerned about that. Whether this is a periodic solid or I just need that there's a reference.
But you could slightly move an atom on a cluster, and the Fermi level would basically.
Okay. Then that's a problem. Exactly. So then that will violate some assumption, and I'd have to sit down and think about which one. Right. You can see I write very few assumptions here to not overcomplicate it, but maybe that's something I should think about.
And I guess another interesting question is whether this will be applied, whether you can apply it to the properties, time-dependent properties in a tight binding, right? Because that, in some limits.
For sure, this result relies on the gap being stable under small changes in the configuration, and so there is. Okay. I think maybe what you're referring to comes from nonlinearity, and then you would need some kind of a stability condition on the response of the electrons.
Right.
This is a result for linear tight binding where I don't need that condition. So I wonder whether that's where we have a clash in intuition, but we can maybe dig into that later.
And sorry, because one more question.
Yeah.
Sorry. And does the background need to be a periodic solid, or can it be a disordered alloy, for instance?
I think it should be. I think you can have it disordered. I'm fairly certain of that. I would be surprised if that would not be true. But I'm now getting nervous, and I need to reread what exactly have we said in the assumptions. See, this is the downside when you're trying to. Elegant and don't write everything down. Okay. We might also have to call Jack and ask him. So all of these results were proven by Jack Thomas, a PhD student who just finished his PhD last autumn with me. Okay. So this is the part that I would now call the modeling in a way, right? So you have your potential energy, and you decompose it spatially into site energies, and then you have a specific representation in terms of other objects, and that's quite a nice step, right? So now comes the next problem, right? So I now want to parameterize all of these, and let's assume I have some magic parameterization that allows me to evaluate each of these terms with just one floating point operation, right? We obviously don't have this, but let's assume you have that. Then you still have a problem because the cost of these sums scales exponentially. Okay, and so that last step, how we overcome that, that's the atomic cluster expansion, and it's when you come from that end here, there's a very simple intuition on how you get to it, and I want to show you this. And then I think I need to be done, and I can't get to the second part of my talk. But anyways, so the key idea is this: that we're replacing these sums here, where we are only looking at every possible cluster once. We do something completely stupid a priori. We just replace that by summing over all cluster n factorial times, but also we're taking into account self-interacting clusters. Yeah, so chemically this is probably weird, I'm guessing, but the point is that we are replacing the sum over simplices in index space to a tensor product domain in index space, and tensor products are so much easier to deal with. That's the key point. So once you have a tensor product domain in these sums, life gets easier. Okay. That is the main idea. So how does that lead to a good method? So and this is my only calculation that I'll show. All the rest will be simple stuff. But I like it so much. I like to show it maybe a bit too often. So now what I do is I take these n-body terms or n+1 body terms and expand them in some basis, right? So what I'm doing here is I'm simply taking a tensor product polynomial. These could be polynomial, a tensor product polynomial expansion of these terms. Okay. And now, because this is a tensor product sum, that's a tensor product sum, I can just exchange them, right? This goes in, that goes out. Now I have a tensor product sum and a product, and because that's a tensor product sum, I can exchange them. I couldn't have done that if I had summed over unique clusters. Yeah, and so what happened is that this sum that goes over n dimensions now becomes a sum over a single dimension. Yeah. So here the cost scales like however many basis functions I have to power n. Here the cost scales however many basis functions times n. Now that is the key idea. And I should acknowledge at this point that basically before I started working with Ralf Trautz, we kind of had everything up to that slide. This was a really his observation that one could do that. The basic idea has been floating around for in many other works in this field even, and since then I've been finding it all over the place. That sort of idea, but he's the one who brought things together like that for interatomic potentials at least. Okay. All right. So a quick summary, and then we'll see if I can add a little bit more at the end. So the way you then actually implement this is you form what is called the atomic density. This is the density of particles in the environment of an atom. You project that density to whatever your basis will be. Then you form these n correlations. Those are these products. This corresponds to the polynomial tensor products. And so at this point, you could say you're done, and there's only one step now left in order to make your life a lot easier, which is the following: that this would actually be a complete basis that would be very efficient to work with. But what it doesn't have yet, it doesn't yet have the invariance under isometries, under rotations and reflections, and that's the last part you now build in to this atomic cluster expansion, which is you take these basis functions and you symmetrize them. It's as simple as that. So you simply average them over all possible generalized rotations, and that gives you the basis for the atomic cluster expansion. Those gives you the features from which you can then build linear models. And I don't know, if you know representation theory, you say, no, you don't do that. There's a classical way in representation theory to do the same thing, which is actually much more elegant, but I find this much easier to understand, and so this is how I usually present it. Okay. And so the key point then here is that this integration need not be carried out on the fly. Basically, these features that you get out, these symmetrized features, they're simply linear combinations of these features here. These coefficients are the Clebsch-Gordon coefficients, and this is essentially well understood stuff for many decades. How to do that in a systematic way, and not just for O3, but any Lie group. You want to symmetrize, there's a way to do it. Okay. So now that we've understood how we construct this site energies, n-body approximation, and now a polynomial approximation of each n-body term, I know exactly what my 3 approximation parameters are. I know exactly in every one of these steps what is the error that I've committed, and then I can put it all together, and I can say the following now. There exists in principle, I don't know how to get it yet, but in principle there exists a site energy. Right? There's the QM site energy, that's the target, and then there's this ACE site energy, this ACE model. And I have 3 terms in my error estimate, right? The interaction range, the body order, and the polynomial degree to which I'm expanding. And sort of for the numerical analyst, here I'm talking about a total degree. So there's additional sparsity in these polynomials which we're exploiting quite heavily. Okay. And there are various other assumptions that go in here that I'm happy to be quizzed on at some point. Okay, and then if you have these 3 approximation parameters, you balance them, you bring everything together, what you end up with is sort of a fun estimate, right? So e to the minus some parameter that doesn't matter. This is the key part, log parameters to 4 over 3. What that tells you is, first of all, there is no curse of dimensionality left in this, right? I've removed everything from that. And this is something you can only do, going maybe back to Gerbo's question, if I dropped the n-body expansion and left only the cutoff radius, this would be false, this result. I do need this. I need both steps. Otherwise, I can't get that estimate. Yeah. Intuitively, just intuitively, where does this come from? Intuitively, you can imagine that. So we have the sparsity, right? I take a sparse polynomial basis, but then on top of that, because of the symmetry, permutation symmetry of the objects I'm approximating, I get an additional n factorial in how many parameters I have. This is actually not true, right? So one has to be really careful there. And so the way you implement this proof in practice is it actually goes into number theoretic ideas, and that was Geneviève Dusson who really worked out the details there. I'm happy to show details later. Okay, so now I can estimate this error in terms of the number of parameters, and now comes the last result that I need, and then I'm done with the linear theory, which says that actually I can evaluate these models, these atomic cluster expansion models, as in some asymptotic limit at essentially twice the number of parameters. So I have one operation to evaluate the basis function and one operation to combine the basis function with the parameter, and that's it. So this is optimal. There's no way to beat this. All right. So this is not just an estimate in terms of how many parameters better, but even the computational cost. And so none of these results I've shown you are quantitative. They're all qualitative. But to me, they kind of give you this sort of feeling of an end-to-end theory that explains why does this model work so well in almost everything we've tried so far. Okay.
The cost means that there is a constructive algorithm with that cost, or there exists.
Sorry, I should have clarified. This is the cost to evaluate this model. I haven't yet told you how I even estimate the parameters. In fact, I am not telling you about how I'm going to estimate parameters. That's a separate talk, and I'm happy to give that some other time. But yeah, so this is only once I have the parameters that achieve this estimate, then I can evaluate that model with this computational cost. Okay.
Environment, right? So that's the cost for one environment.
That is the cost per atom. Yes. Sorry, that's a good point, right? So if you have 1 million atoms, then you have.
So it's linear scaling.
Well, not just linear scaling. I mean, this is my point. Oh, yeah, no, totally. Yes, it's of course linear scaling in the number of particles you have. Absolutely. Okay, and the locality matters in this, right? Without locality, you can't do this. Okay, so I now need to make a decision on what I will say, but I think just to maybe point this out quickly, since the first results and sort of some of the first theory papers that we've been working on, this has become really a very close collaboration between Ralf Traut, Gabor-Chani, and I, and our groups, and more and more coming out. But I'll maybe move just through a few examples to show you what we can do. So I think many people will know the gap potential, and that was the first thing that we tried. Let's take a really an ambitious training set, silicon. The gap for silicon is essentially the entire phase diagram. There's not much left, I think, that you could want to model. Can we reproduce gap accuracy? Yes, absolutely. So this is on different properties of silicon tested gap against ACE, and we match the accuracy in every single one at a really much lower cost. And much harder to show here, but much harder to quantify, but we also get the impression that the generalization properties of the ACE models are much better. But this is still something we're working on to figure out how it can be done. What else could I show? Here you can sort of see this maybe. This is when you take, what happens here, you take a slab and then you basically cut it in the middle, and then you move apart the two planes, and so you see this oscillations in the stress for the gap potential, whereas we hardly ever see these with the ACE potential. That's sort of where our intuition comes from. One really impressive test that gap does is this random structure search, where you say you initialize your potential in random configurations and see what does the optimization converge to, and can you roughly match DFT, and basically I think the gap potential and the ACE potential are the only ones we've ever tested that can do this. Anyhow, so everything I've said so far ignored species, but adding chemical species to this is not difficult. You simply have to add an extra parameter to each site. You have the position and the species, and that's about it. And then you can do, for example, alloys. Here's a titanium, a very small. There's a very, very, very early test on this. A titanium alloy. You can do molecules. We can see how well do we fare against the standard methods on molecules. And just because I'm going so slowly, I want to skim over these a little bit. But this is one that I can't skip because so that's a student of Gabachani's who's really been pushing this question of how can we fit alloys. And to get this figure, much more goes into this. So there's this technique we've been working on, which we call hyperactive learning. It's essentially a twist on reinforcement learning, but the details, I'm happy to talk to anybody who wants to see them. But so this was generated. This is now what you can see here are 3 phase transitions for, I don't know. Are you allowed to call this a high entropy alloy already? Maybe. And so you have significant chemical complexity. This was produced with nested sampling. For those of you who know that, this is an insanely costly sampling algorithm. The fact that we can do this with a machine learned potential in the first place, I think, was surprising. That means we can really get away with very sparse ACE parameterizations here. The training set for this was generated fully automatically. There's almost no user intervention in this. And still, we can get these robust fits that allow you to do nested sampling, which really explores a huge amount of configuration space. So we're getting more and more happy, let's say, put it this way, with our simple box standard linear ACE models. Like everything up to this point was linear modeling. We're saying we can go from DFT to interatomic potentials with just linear models that are, we put a bit of care into how we construct them, no neural networks, no nonlinearities, nothing like that. And so as a result, there's just a lot that we control in the regression task, especially where this becomes beneficial. And basically all of these fits that I've shown you, I could run on my laptop in a few hours. I could generate the fits on my laptop in a few hours. I don't need any hardware for that.
Just say a bit, how do you do the regression problem? And you said
sure.
It's not a talk, but maybe you can just summarize it in 1 minute.
I can do it in 10 seconds. Linear least squares.
Right, but you regularize.
Yes, so that's the caveat. That's where the art goes in. So there I have to admit this is still an art. For example, do we use rank revealing QR because that's really good sometimes, and then sometimes we're better off using LSQR, regularize it, but also truncate it early. And so part of why I'm not talking about that is because I feel it's still an art. And anyhow, okay.
That depends on the system that you want.
Exactly. Yeah. For example, do you have an overdetermined system, an underdetermined system? So Cass is heavily sparsifying now. He's using a scikit-learn algorithm, relevance determination, in order to sparsify our basis sets even further than we do it a priori. And that has made a big difference. So at the moment, it's a big bag of tricks. Maybe in 2 years, not anymore. I really hope so, but I'm not going to promise that. Okay. Okay, so where is all this going? So I want to take 2 minutes to talk about this stuff. And specifically what I'll talk is about tight binding. So this is...
You still have time. You still have 12 minutes.
Yeah. There's lots coming. This is now the fun part, right? Everything up to here is what's done, and we're happy with this. And now I wanted to talk about things that I'm very much thinking about on a daily basis, and where I was generally hoping there'd be scope for discussions, for interesting discussions after this. Yeah. Okay. But basically, the point is in all of this, everything I talked to you about, this locality is important, the reducing dimensionality, the body order expansion is important, these sparse polynomial approximations, which I didn't really talk about, which maybe I should have. The one thing that changes is instead of invariant properties, you now have equivariant properties. So And sort of this is the first comment I want to make quickly. Right? For example, if you have a Hamiltonian operator, that's not invariant. Under rotation of the structure, it's equivariant. Yeah?
Can I ask a question related to what Alex asked earlier? Although the proof is at the linear level,
yeah.
It means that, metal is simple metal is the hardest thing.
Yeah.
There's no gap. But in practice, when you do this calculation, I guess you can handle metal without any problem.
Yeah.
Right.
That is a very, very good question.
Yeah,
I have no idea why.
But this is indeed the case.
That is indeed the case, yes. Metals are simpler than most other materials. Yeah.
And I guess that's because of the strong screening effect.
Yeah, so that's right. So you get the screening. So that means doing this here is justified in the metal, right? Putting a U-cover potential.
Finite temperature metal, just to be finite temperature, not.
Yeah, but the finite
temperature. Need finite temperature.
No.
This is totally in the nonlinear.
Okay, can I?
In practice.
Okay. So there are two issues here, right? You get non-locality in a metal. So the one that comes from, for example, the Coulomb interaction, that goes away, right? That's not important. Do you agree?
It's not like I know a proof. I'm just saying that.
Yeah, that's right.
Okay, then let's leave the discussion.
This is not about the proof. This is just talking about observation.
But I'd be happy actually to talk about it later because it's something I thought I understood at some point and now I think I don't. So I'd be very happy to talk about this later. Yeah.
But you could have charge density wave materials where this locality goes away, right? But not in normal metal. Normal metals are probably.
I'm happy to learn more. So I'll take 2 seconds to explain why it really does not matter whether you want to fit invariant or equivariant properties. This was how you construct the ACE model for invariant properties. You form the atomic density, you take the n correlations, that sort of corresponds to an n-body basis, and then you symmetrize them. Everything up to here remains the same, right? Because every property can be expanded in these. And now the only thing that changes is instead of, you have to be careful about how you average. And essentially all you need to do is you need to bring in whatever form of equivariance you need into this averaging process, right? So just as an example, if you need a Euclidean covariant vector, then you simply take a basis in this space R3. You say, what is the action of a rotation on the vector? Well, it's q times the vector. You bring that in your averaging and you're done. That's literally it. All of that can be incorporated in our models without any problems, has been done, is implemented, is available if anybody wants to use it. Yeah. Okay, so one of basically the first thing that we tried with that, actually it's the second thing, the first thing didn't go so well. The second thing we tried is, can we fit a Hamiltonian? And so it's basically this thing here. Okay, but now there's no U-cover. This is really full FHI aims, actually, so what we're doing here. And many of you will know Reinhard Maurer. He's the one who designed the reference DFT/tight binding model here. And so the question we asked is, can we fit not the Hamiltonian itself, because I mean that's easy, but can we fit the self-consistent Hamiltonian? So you first solve the self-consistent field iteration, and then you get an output Hamiltonian, and can we fit the blocks in that Hamiltonian directly using an ACE model? And so sort of what this looks like, every block in the Hamiltonian then has a few s orbitals, p orbitals, d orbitals, and then each of these blocks in here would be its own linear ACE model with different equivariances. Right? So you expand each of these blocks into your equivariant ACE spaces, you do a linear least squares, and you're done. And so I'm maybe a little embarrassed showing this because I think it's an extremely, extremely simple toy problem, and it no more shows than, in principle, the methodology we have does something sensible. As we increase the complexity of the model, the Hamiltonians converge, and if we go high enough, then we can reproduce band diagrams, densities of states at high accuracy. Okay, and what was this? Just elemental aluminium, not a difficult problem, but this field moves so fast. If you don't publish small steps, then you're suddenly a year behind, right? That's pretty much it. Why we published it with that, but we're constantly looking now for more interesting results of that kind. All right, so we can do things like that with just these linear ACE models. And you said 8 minutes, so I will skip equivariant networks. This is really a fun thing. Essentially, you can use A's to build equivariant networks. That's the 1-second version of that slide. This is something that I enjoy thinking about a lot, because this is now all the sort of things I'm now really that actively thinking about how can we further improve our ACE models. And the question really is, how can we make them even more efficient, even more robust, scale to more interesting systems? That's where this comes from. And so, for example, when you go back in Ralf Drautz's first paper, he actually, yes, he proposed a linear ACE model, but he said, actually, we should really do the following. We all know Finis-Sinclair is a fantastic model, so let's just write down Finis-Sinclair, but instead of putting a pair potential here and a pair potential there, I put an ACE potential here and an ACE potential there, and you get very nice results with that, actually. And because your nonlinearity is now explicit, you're not learning it, this is what I would call a mild nonlinearity, your regression task becomes much, 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 much easier than for deep neural networks. Okay, so why does this work so well? And so it turns out, actually, if you remember our result for linear ACE models for the body order expansion, right? That was it. Yes, exponential, but then we had this enormous caveat here that we can only do this for a single crystalline phase disproof. It turns out that if you do something like that, you need to extend it a bit. So basically what this is, it's the first term in an expansion, yeah? And if you take this to n terms, then you end up with an n-body potential where with an embedding function where it's explicit. You can write down what that is. And in this case, you get the same result qualitatively, but now this would be true uniformly across all phases. And so just intuitively, when you shift the gap somewhere else, you need to adapt your approximations. And the nonlinearity allows you to do that. That's what's behind this. It becomes a nonlinear approximation scheme, and I don't see a way without that to achieve something like this. Right? So basically, these physical nonlinearities, there are generic physical nonlinearities that, at least in theory, hugely improve your results, and in practice sometimes as well. So for example, Yuri, in a postdoc in Ralph's group, he fitted there's this benchmark paper which you can think about these training sets whatever you want, but it's fun to compare, right? And so okay, can we bring the curve lower? Yeah, with that we can bring the curve low and to the left, right? So you get these very fast, very accurate potentials with that Finis-Sinclair idea. By comparison with the linear ACE model, I put some extra dots here just a few days ago to see where it would fall. It's not bad, but you don't quite reach the same cost accuracy ratio as with the nonlinear models. And if there are more questions, I'm very happy to take them. Thank you.